Hi everyone. In this module we will look at the motion of rigid bodies. A rigid body is any object that has a definite size and shape. Previously we would have looked at translational motion of these rigid bodies by considering the motion of its center of mass or treating it as a point particle. And we found in the previous module that this is a valid approach because the net force will cause motion of the center of mass of the object. In this section, we'll also consider rotational motion of the rigid bodies. An object can undergo translational motion or rotational motion or both at the same time. Okay, let's review that for an object moving in uniform circular motion, we found that its speed, v, was 2 pi r, so 2 pi times the radius, which is the circumference of the circle, which it makes in one period, which is the time for one cycle of the motion. And this gives us a constant or an average speed in meters per second. A new quantity that we can use for rotational motion is the angular velocity omega. Omega equals v over r, so that translational speed over the radius, which is equivalent to 2 pi over the period. And this angular velocity is really the average angular velocity or constant if we have a constant speed. And the units are going to be radians per second. Usually radians is a unitless quantity, but often in physics we do write radians just to be explicit about the units. Note that if you have any angular displacement in degrees, you can convert to radians by using this conversion factor, 180 degrees equals pi radians. We may need that because this angular velocity is a measure of the rate of change of the angular displacement per unit time. So just some notes on this. If an object is rotating, then all parts on that object will rotate with the same angular velocity. If you picture a disk spinning, this means that all points on the disk complete the same angular velocity or the same angular displacement in the same unit of time. However, since all points on the disk are different distances from the center, they would not all have the same speed. And that's why it's often more useful to use angular velocity and angular quantities when looking at rotational motion than the translational variables that we've seen before. In rotational motion, we'll often make use of the polar coordinate system. So the polar coordinate system uses variables z, r, and theta. So if you look at this diagram, I've drawn a rotating object here. So we have the axis of rotation at this endpoint, and it's rotating around that point. R is a position. It's the radial position from that axis of rotation. Then we have theta, which is the angular displacement in radians from a zero reference point. So it would have a zero axis just as any of our translational variables. And then z is the coordinate measured perpendicular to this plane of rotation. So it would be here into or out of the page, and z would be a position along that third dimension. Okay, one more variable or one more equation that is used here is arc length. The arc length s equals r delta theta. So if an object travels through a rotation angle of delta theta, it moves through an arc length s, which is r delta theta. And we can see if it made the whole circle, then that would be r times 2 pi, which gives us back the circumference. All right, one more thing before we get into the examples. Okay, let's look further into angular velocity. So as we saw before, the average or the constant angular velocity, if it is constant, is 2 pi r over the period. We can also find that by taking the angular displacement per unit time. So delta theta over delta t, which is theta f minus theta I over tf minus ti. And again, that gives us units of radians per second. So if we want to find the instantaneous angular velocity, like we did with any of our variables before, what we can do is take the limit as delta t goes to 0 of delta theta by delta t, which gives d theta by dt. So the derivative of the angular position per unit time gives angular velocity. Now notice that I've labeled this with a z here. That z is to show that if the object is rotating in the xy plane, then this angular velocity is directed in the z plane, the perpendicular plane. So however this object is rotating, the angular velocity is along its axis of rotation, which is in that third dimension. And there is a sign convention here that's used for angular velocity. Basically, it's counterclockwise motion is positive and clockwise motion is negative. But you can find this using a right-hand rule, very similar to what we did for the magnetic field surrounding a current. So what you would do is curl your fingers in the direction of the rotation. So for this counterclockwise rotation, we curl our fingers that way, and then the direction your thumb points is the direction of the angular velocity vector. So it is a vector, just like any velocity. Okay, so that's the positive z direction, which is positive, and now if you look at clockwise, we're going to curl our fingers the other way, and my thumb will point downwards, which is in the negative z direction. So that's why we have negative for counterclockwise rotation. One more thing is that angular velocity can also be measured in RPM, so that means revolutions per minute. In that sense, it's more of an angular frequency. And to do that, we take 1 radian per second and multiply. One full revolution is 2 pi radians, and then multiply to convert 60 seconds to minutes. So you can do this little conversion to get RPM, which means revolutions or rotations per minute there. Okay, let's look at some examples. An airplane propeller is rotating at 1900 RPM. How many seconds does it take for it to turn through 35 degrees? So why don't you pause and try that? All right, have a look at the board. So we're given our angular velocity, which is 1900 revolutions per minute, or RPM. And so we do need to convert all units into radians and seconds in questions like this. So we'll multiply, as I showed you before, by 2 pi radians over 60 seconds to convert this into radians per second, which gives me 199 radians per second. Okay, and then delta theta, it moves through 35 degrees, which we can convert into radians by multiplying by pi over 180, and that's 0.611 radians. And then lastly, we can apply our formula for average or constant angular velocity here. Omega z is delta theta over delta t, and solving for delta t is delta theta over omega. So the 0.611 radians that we converted over 199 radians per second gives me 0.00307 seconds. So that's how long it takes to turn through that angular displacement. Okay, next example. A particle moves clockwise around a circle at a constant speed for 2 seconds. It then reverses direction and moves counterclockwise at half the original speed until it has traveled through the same angle. What is the particle's angle versus time graph? All right, so I've sketched out these graphs here. We know that it breaks after 2 seconds and then returns to the starting point. So we do know wherever it starts, it has to return to that position. So that can tell us which graphs here are an option. Based on that, it has to be either B or D, because both of these graphs return to the same 0 position where it started. The second point is that we're told that it moves clockwise for the first 2 seconds. So remember this, I'll just write in the middle here, d theta by dt. Our angular velocity is negative if the displacement is clockwise. So we have it rotating clockwise, which is a negative angular velocity. And on a graph like this of theta versus time, this is the slope. So we know if it's clockwise, it has to have a negative slope for the first 2 seconds. After that, it reverses, so its slope should be positive after that. But this is B, right? So this is our negative slope for the first 2 seconds, then it reverses direction, now it's going counterclockwise, and then it returns to its initial position. So B is the correct graph in this case. If the angular velocity is not constant, then as the object rotates, it will have an angular acceleration. And this is defined very similar to what we did for linear translational acceleration. So alpha is the symbol here for angular acceleration, and to start out, the average angular acceleration, or constant, if it's constant, alpha average z, is delta omega, so the change in angular velocity per unit time. Again, that's omega f minus omega I over tf minus ti. The units here for angular acceleration are radians per second squared. I've written that here. And if we want to find instantaneous angular acceleration, just as we would with linear acceleration, and as I showed before, to get to angular velocity, we take the limit as delta t goes to 0. So we get d omega by dt, which is also the second derivative of the displacement per unit time. So d squared theta by dt squared. And so just a note about the sign convention here for alpha, the angular acceleration. Notice I have z again. That's because it's also a vector along the z-axis, so perpendicular to that plane of rotation for the object. And its sign behaves like any acceleration does with velocity. So if omega, the angular acceleration, and alpha have the same sign, that means that the object is speeding up. So for example, we could have counterclockwise rotation with a positive angular acceleration. That means that it's speeding up. Or we could have clockwise rotation with a negative angular acceleration, and this would still mean that it's speeding up. So maybe it helps to think about counterclockwise as a positive direction, and then everything is as it was for our translational quantities. And then, so if alpha and omega have opposite signs, then the object is slowing down. So this could be for counterclockwise rotation with a negative angular acceleration. That would mean slowing down. Or clockwise rotation with a positive angular acceleration. That would be slowing down as well. All right, let's do one more example. The angular velocity of a flywheel obeys the equation omega z at t equals 2.75 radians per second plus 1.5 radians per second cubed t squared. A, what is the angular acceleration of the flywheel at t equals 0 seconds and t equals 5 seconds? B, through what angle does the flywheel turn in the first 2 seconds? Okay, let's look at part A first. So I've drawn the function up here. We have omega z, 2.75 radians per second plus 1.5 radians per second cubed t squared. And let's start by finding the derivative so that we have the angular acceleration function in general. So alpha z at t is d omega by dt. So this derivative of the first number is a constant, it's just 0. And then we have the exponent, so 2 times 1.5, which is 3. And then dropping the exponent on the t, it's just t. I know you know how to do the derivative by now, but okay. Then alpha z, we can plug in t equals 0, and we just get 0 radians per second squared here because of the t. And then alpha z at 5, we're plugging in 5 seconds for t, so we have 3 times 5, so 15 radians per second. All right, I'll just pause so I have some space for part B. Okay, so now we want to find through which angle does the flywheel turn in the first 2 seconds. So let's go to our angular velocity formula because that's where we have d theta, the change in angular displacement during that time. So omega z equals d theta by dt. Which we can rearrange to get d theta by itself. D theta is omega z dt. And then to get theta, we're going to need to integrate both sides. So we'll integrate from our limits theta I and theta f and ti and tf over both sides here. Now, when we do this, also we were given the angular velocity function, and just like translational, we know that starting with velocity in order to get a displacement or a change in position, we need to take the integral. So that's all we're doing here. It's just now rotational quantities. Okay, so on this side we'd have theta f minus theta I, which is delta theta, and that equals this integral, and this is our function that we're given in the question. I've just written it there. So we want to integrate that from 0 to 2 seconds. So integrating here, it's a constant, so multiplying by t, and then here raising the exponent by 1 to t cubed, and dividing by that 3. And then this is from 0 to 2 seconds. And notice all of these terms at 0 will be 0. So delta theta, or theta at 0 is 0. And then here we get 2.75 times 2 seconds plus 0.5 radians per second times 2 seconds cubed. And then calculating that gives 9.5 radians. So what we're seeing is that all three quantities have the same relationships we've seen before. So if you start with position, you take the derivative, so angular position, take the derivative to get the angular velocity, and the derivative again to get the angular acceleration. And then going back the other way, starting with angular acceleration, we could take the integral to find the angular velocity or the change in angular velocity, and then take the integral in order to find the change in angular position. So everything that we're comfortable with applies here for rotational motion. All right, that's all for this section. Let me know if you have any questions.